So the second scale that we have, right? So first scale we have the empirical centigrade scale. So the second scale that we have, number 2, is the thermodynamic scale of temperature. So it is called the thermodynamic scale. It's the thermodynamic scale of temperature, right? Okay, so the thermodynamic scale of temperature. So there are 2 fixed points on the scale, right? So we have 2 fixed points on the scale, 2 fixed points, right? Which are, so the first one, right? The first one is the absolute zero. It's called the absolute zero, which is 0 Kelvin, right? So what is the absolute zero? This is the lowest possible temperature. So this is the lowest possible temperature. Lowest possible temperature, right? So it's 0 kelvins or minus 273 degrees Celsius, right? B, the second fixed point is called the triple point of water. Called the triple point of water. So this is 273.16 kelvins. So what is the triple point of water? This is the temperature. So the triple point of water is the temperature at which ice, right? We have ice, water, and water vapor. So all the 3 states, right? Ice, water, and water vapor are in thermal equilibrium. So they are coexisting. The 3 states are coexisting, right? So, so by measuring the gas pressure at triple point, right? So we know that by measuring the gas pressure. So by measuring the gas pressure at triple point, right? Say PTR, right? And at unknown temperature, T, right? The pressure P, right? So, which means then the unknown temperature, right? The unknown temperature, which means the unknown temperature in kelvins is given by the equation T is equal to 273.16, right? Times pressure at unknown temperature over pressure at triple point. So that is the equation that gives us the unknown temperature in the thermodynamic scale of temperature, right? So, so that's the equation. So decreasing the pressure of the real gas, right? If we decrease the pressure of the real gas, it behaves as an ideal gas, right? So, and then we know that for an ideal gas, PV over T is equal to constant, right? Where T is the thermodynamic temperature. Okay, so how do you convert kelvins and degrees Celsius? So we know that temperature in degrees Celsius is equal to absolute temperature in kelvins minus 273.1.15. Okay, so theta is equal to T minus 273.15, right? Which means T is equal to theta plus 273.15. So that's what it means. Temperature in kelvins is equal to temperature in degrees plus 273.15, right? Now I want to look at the different thermometers. So now I want to look at the different thermometers. Now that we've looked at the two temperature scales. So that's a liquid in glass thermometer. So that's a liquid in glass thermometer, right? So that's the liquid in glass thermometer, as you can see here. So it consists of a glass bulb here, and then this black stuff, right? This is the liquid, which can be alcohol or a mercury, right? So we usually specify whether it's mercury in glass or alcohol in glass. So this is the capillary tube, right? And then this is the glass stem, right? Let me just, so this is the glass stem, right? Here it's called the glass stem. So the glass stem, right? And then these are graduations, right? So these are graduations on the thermometer. So these are the graduations, right? So the liquid in glass comprises of a glass bulb that contains the liquid, right? And the expansion of the liquid makes its thread in the capillary tube. So there's a thread in the capillary tube, right? To increase in length and measure the temperature, right? So with regular use, what you need to know is with regular use, these thermometers become inaccurate because the frequent use causes the expansion of the glass, right, to become permanent. So that's why they become inaccurate with time, and they need regular changes. So because the scale of the temperature would have been affected, right? So that's the liquid in glass thermometer, right? Moving on. So thermocouple thermometer, right? So a thermocouple thermometer looks something like this, right? So it's remember we said it requires a millivoltmeter, so it's something like this, right? And then it is something like, right? So this is wire Y, and then this is wire X, right? So this will be at 0 degrees Celsius, right? Okay. So and then this is the temperature. So this is the temperature probe, right? Okay. So the thermocouple is made by twisting two dissimilar metals, right? So we know that the thermocouple is made by twisting two dissimilar metals. So two dissimilar metals to make two junctions, right? So there are two junctions, make two junctions. The reference point, which is 0 degrees Celsius, we have marked here, and the temperature probe, right? So the two junctions here and the temperature probe, these are the junctions, right? Here, the junction here and the junction there, right? So when the two dissimilar metals are brought in contact, free electrons pass between them at the contact points, right? So here, free electrons will pass through at the contact points. So, but because the electrons can leave one metal more easily than the other, a PD develops across the junction. So there's a potential difference due to the tendency of electrons to leave easily and using the other metal. So it's easy for electrons to leave the other metal than the other. So a PD develops, right, across the junction. So the free ends are not twisted. That are not twisted are joined to a millivoltmeter or a potentiometer. The reference junction is kept at ice point or suspended in air. So that's a thermocouple thermometer. So the millivoltmeter is to measure the potential difference across the wires, right? So that's the thermocouple thermometer, right? Now we want to look at the resistance thermometer, right? Want to look at the resistance thermometer. Resistance. Okay. So we have the resistance. We have the resistance thermometer. Yeah. Okay. So this is the resistance thermometer. It's okay. So it's something like this, right? So it's resistance thermometer, something like that. And then we have right here where we have wires here. So there's wire here. Okay. Okay. So we have wire here like this. And then we have, let me just, yeah. Okay. So that's and then there's a wire here. So you go and look at the proper diagram. This is just uh, then these are copper leads, right? Copper leads. And then so there's a liquid in here, there's oil in here. So there's oil, right? So these ones, right? So these ones, there's what we call a Wheatstone bridge. So there's what we call a Wheatstone bridge. So these are the wires that are connected to the Wheatstone bridge, right? So and then to the Wheatstone. So and then this one is connected to the dummy leads. Dummy leads to bridge, right? Okay. So that's it's a rough sketch of the resistance thermometer, right? So the measured resistance is that of a platinum wire, right? So the resistance that we measure is that of a platinum wire and a Wheatstone bridge, right? So it's that of a platinum wire and the Wheatstone bridge, right? Which is used to measure its resistance, right? So for very accurate measurements, resistance of the leads between the bridge and the platinum wire are compensated by connecting dummy leads in the other arm of the bridge. So that's how the resistance thermometer works. So a resistance thermometer it's a robust thermometer, right? Resistance thermometer and a thermocouple thermometer. So these are robust thermometers. So you go and look at a nice diagram, right? So that you can appreciate. This was just a rough sketch. So let's move on to the constant volume gas. That's the constant volume gas. The last thermometer we're going to talk about is the constant volume gas, right? So this is the constant volume gas here with dry gas in bulb side. So the dry gas could be just air or a gas that behaves almost ideally, such as nitrogen, right? So you use nitrogen right here. Then there's the now glass tubing here. Then this is the fixed level of fluid here, right? So the gas pressure here. So there's gas pressure here. So the gas pressure will be equal to rho GH plus atmospheric pressure. So it will be rho GH plus atmospheric pressure. Right? So the H here that we use is the H here, right? So this is the H between this fluid level and this fluid level, the height. So it's sort of like it's manometric properties. So the constant volume gas incorporates the manometric properties, right? Right. So temperature readings, so these are sometimes called ideal gas temperatures because we use a gas that behaves almost ideally. So they're sometimes called ideal gas temperatures. So there's sometimes called ideal gas temperatures, right? So that was a quick look at the different types of thermometers, right? So now I want to compare the thermometers, right? The four thermometers, right? So just draw a table here. We just draw a table. So we have type of thermometer, right? Type of thermometer here, and then we have range. So we have the range, right? And then we have the advantage. Advantage. So once looked at that, right? When we're introducing the topic, once looked at that, but disadvantage, right? So it's a 4 columns table like this. Okay. Okay. So the first one we're going to look at the mercury in glass. So now we have specified mercury in glass, no longer liquid in glass, right? So the range for mercury in glass is 234, right, to 723 kelvins. So that's the range of the mercury in glass. So what is the advantage of the mercury in glass? Right, it is portable. So the mercury in glass is portable. It is convenient, right? Convenient. It is also easy to use. So anyone can use a mercury in glass, right? That's why you use it in our practicals. So the disadvantage, what disadvantage is a mercury in glass, right? They are fragile, right? You know that it's a limited range, right? It's a limited range, 234 kelvins to 700. It's a limited range, right? So these are the advantages and disadvantages. Then we're going to look at a thermocouple thermometer. So a thermocouple, the range has increased 903 to 1336 kelvins, right? So the advantages of a thermocouple, it is a fast response. So that's what you need to know. So it's a fast response, right? So it's suitable for rapidly changing temperatures, right? So it's got a fast response. We have remote reading, right? Remote reading, right? And also is a wide range. So that range is wider, right? So it's wide range. So the disadvantage is as we already mentioned, that it requires a millivoltmeter, right? It requires a millivoltmeter. So that's the disadvantage. Tinenge tichida kutoshandisa nemillivoltmeter. Okay. So the third thermometer we're going to look at is the resistance thermometer. So the resistance thermometer, the range for a resistance thermometer, right? It's 90 to 903 kelvins, right? So the resistance thermometer is accurate, right? So that's what you need to know, it's accurate. So it is best used for small temperature changes. So best used for small, very small temperature changes. So if you want to measure very small temperature changes, your resistance is your go-to temperature changes. Okay. So the disadvantage, mind, is that it is slow to respond. It is slow to respond. That's the disadvantage of a resistance thermometer, right? Probably because it is bulky, as you saw earlier, with the dummy, the oil, it may take time to respond, right? So it needs steady temperatures. right? Small but steady temperatures. Okay. And then the thermocouple is the one that is fast response, rapidly changing temperatures. So the last one, the constant volume gas. I want to look at the constant volume gas. So what's the range of the constant volume gas? Right. So this is below 90 kelvins, below 90 kelvins, right? So the advantage is that it is accurate. Constant volume gas is accurate. It has got a wide range, right? Okay. So it gives ideal gas temperatures directly. So the main advantage that it gives ideal gas temperatures directly. Ideal gas temperatures directly. So that's what you need to know, right? Gives ideal gas temperatures directly. So the disadvantage that it is bulky, right? It is bulky. So that's the disadvantage, right? It is slow to respond. So if it is bulky, which means it is slow to respond, right? Slow to respond, right? And it is inconvenient because of its bulk, it's not portable. So it is inconvenient. Right? Sorry for the spellings. Right. So that's on temperature. Right. So that's what we had on temperature. The 4 types of thermometers, right? There are thermometric properties. So what you need to know, right, is the 4 types of thermometers, right, that we have, right? The thermometric property, thermometric substance that they rely on, right? The advantages and disadvantages. So you need to be aware about the advantages and disadvantages of those 4 types of thermometers, right? And also remember the scales, the 2 scales that we have, the empirical centigrade scale of temperature, and then we have the thermodynamic scale of temperature, right? So for the thermodynamic scale of temperature, where we have the 2 fixed points, right? The absolute zero and the triple point, right? So that's the end of our lesson. If there are any questions,